In this lecture, we shall develop a method to find out the principal axis coordinate system of a rigid body. Earlier, we have remarked that if we have a symmetric bodies, then from a symmetry consideration, we can find out the principal axis coordinate system in which the product moment of inertia are zero. As for example, if we have a square lamina, uniform square lamina, then any coordinate system which is centered at the center of mass of the lamina and the axis parallel to the edges, um, and the third axis is perpendicular to the plane of the lamina, it can be treated as a mm, principal axis because the product moments are zero in this coordinate system. But if we don't, if we have a body whose symmetry axis is not that obvious, then how to find out the principal axis coordinate system? We shall describe this technique taking square lamina and a cube as an example. This is done just in order to keep the mathematics simple. uh, we know that if we consider any coordinate system as then in S coordinate system I have moment of inertia is the Ixx, Ixy, Ixz, Iyx, Iyy, Iyz, Izx, Izy, and Izz. This is the form of the moment of inertia tension in S frame. Now we consider a body fixed frame, that is we have a body fixed frame S frame. So this is the PSCS coordinate system. In PSCS coordinate system, this reduces to ID is equal to I1 0 0 0 I2 0 0 0 I3. So the moment of inertia tension becomes a diagonal. So how to get this PSCS coordinate system? We consider the eigenvalues of this. These are the eigenvalues of this matrix. It is being a real symmetric matrix, so Hermitian matrix, so eigenvalues are real and the eigenvalues are I1, I2 and I3, and correspondingly we have eigenvectors E1, E2 and E3. These eigenvectors are the axis of the PSCS coordinate system, and when we express this matrix in this coordinate system, it assumes this form. This is the finding out the PSCS coordinate system is nothing but the eigenvalue problem of a matrix. We start the so we firstly consider a uniform square lamina. Determination of PACS principal axis coordinate system. One is the example, first example that we are going to discuss is a square lamina. The square lamina is like this. It is the uniform square lamina. We choose one corner of it as the axis of Cartesian coordinate system, so that it is the square lamina. Thus, you consider this is the x-axis, this is y-axis, so the z-axis is in this direction. we have chosen the coordinate system such that the origin lies at one of its corner. The x and y coordinate axes are parallel to the edges of the lamina. That is, the lamina lies in z is equal to 0 plane, and z axis is perpendicular to the plane of the lamina. So for this lamina, for the lamina z is equal to 0 identically. So what is Ix? Ixx is equal to originally this was the surface integration. First let me calculate if m be the mass, then sigma surface density is mass upon s square. So this is integration over ds, where ds is a small volume surface element, which is dx dy. So this sigma ds times y square plus z square, and since z is equal to 0, this is sigma integration over dx from 0 to a, y square dy from 0 to a. So this is a, and this is sigma a 1/3 a cube. So this is 1/3 ms square. By symmetry, this is also the value of Iyy due to the symmetry, and Izz can be calculated as this: sigma ds x square plus y square. If we calculate it like this, we will have, this is 2/3 ms square. Alternatively, we can use perpendicular axis theorem to get this. Now Ixy is equal to minus sigma ds xy. So this is minus sigma x dx from 0 to a, y dy from 0 to a. So this is minus 1/4 sigma into the power 4 is equal to minus 1/4 ms square, and this is equal to Iyx. And other quantities, that is Ixz is equal to 0 is equal to Iyz, because they involve z in their in the integrand, and z is equal to 0 for the lamina. So in S frame, the moment of inertia is ms square taken common. This is 1/3 minus 1/4 0 minus 1/4 1/3 0 0 0 2/3. This is the moment of inertia tensor in this coordinate system. Our aim is to find out the principal axis coordinate system. Let the eigenvalues be, let the eigenvalues are I is equal to lambda ms square. So the secular determinant which comes out to be 1/3 minus lambda minus 1/4 0 minus 1/4 1/3 minus lambda 0 0 0 2/3 minus lambda. This is equal to 0. This is the characteristic equation or secular equation. So this is this, and if we expand to this term, So we have 2 by 3 minus lambda taken common, it is here and there, and this square minus 1 minus 4 whole square. So we have two factors. One is 1 by 3 minus lambda plus 1 by 4, and 1 by 3 minus lambda minus 1 upon 4 is equal to 0. Or 2 by 3 minus lambda, this part is 1 by 12 minus lambda, and this is 7 by 12 plus lambda, and this is 1 by 12 minus lambda is equal to 0. So the lambda values are lambda 1 is equal to 1 upon 12, lambda 2 is equal to 7 upon 12, and lambda 3 is equal to 2/3. So our problem, we have come to this conclusion that this is the matrix, and the eigenvalues are I1 is equal to 1 upon 12 ma square, because these are the lambda values. So eigenvalues are I2 is equal to 7 by 12 ma square, and I3 is equal to 2 by 3 ma square. Now we want to find out the eigenvectors. We write the eigenvector like this. I matrix operating on the ith eigenvector gives us II, EI, where EI is a column matrix, and we write it as E1I, E2I, E3I. So for I is equal to I1, I is equal to I1 is equal to m square by 12. This is the first eigenvector. We have these terms of diagonal terms remains unchanged. The diagonal term changes. The diagonal term is, we have 1 by 3. This is 1 by 3 minus 1 by 3 minus 1 by 12 minus 1 upon 4, 0, minus 1 upon 4, 1 by 3 minus 1 upon 12, 0, 0, 0, 2 by 3 minus 1 upon 12. This is multiplied by E1, 1, E2, 1, E3, 1, this equal to 0. This much as minus 1 by 3 minus 12 is 12, 4 minus 1, so this is plus 1 by 4. So this is plus 1 by 4. This is also plus 1 by 4. And this part is 2 by 3 minus 1 by 12 is 12. This is 7 by 12. So this part is 7 by 12. This is the new form of the matrix. And now, if we carry out the matrix multiplication, we see that E11 minus is equal to E21 and E31 is equal to 0, because if we first equation this multiplied by E31 is multiplied by 0, in the second equation it is multiplied by 0, the third equation, this multiplied by this 0, this multiplied by this 0, and this one multiplied with the right hand side is 0, so E31 is 0. And so we see that the normalized eigenvector E1 is simply half times 1, 1, 0. Now if we write I is equal to I2 is equal to 7ms square by 12. Note that this factor was originally 1 upon 3 minus 7 by 12, and this one was 1 by 3 minus 7 by 12. This was 2 by 3 minus 7 by 12. This is E22, E32. This factor 1 by 3 minus 7 by 12, 4 minus 7, so this is minus 1 upon 4. And this factor 2 by 3 minus 7 by 12 is equal to 12. One by 12. Again, we see that E21, E12 is equal to minus E22, and E23 is equal to, sorry, 32 is equal to 0. 32 is equal to 0. So the normalized eigenvector, second eigenvector is 1 upon root 2, 1 minus 1, 0. These are the two eigenvectors we have obtained. Now lastly, for I is equal to I3, I is equal to I3, and this is 3 by I3 is equal to 2 by 3. This factor will be, this is 1 by 4 as it is, so this is 1 by 3 minus 2 by 3. This is 1 by 3 minus 2 by 3. This is 2 by 3 minus 2 by 3. So this is 0. So that, sorry, this is minus 1 by 3. This is minus 1 by 3. And this is 0. Here, the E33 main is no more 0. So this is the matrix. So if we multiply the first one, we have 1/3 E13 plus 1 by 4 E23 is equal to 0. For the second equation, 1 by 4 E13 plus 1 by 3 E23 is equal to 0. If we work out that, we see that E13 is equal to E23 is equal to 0 is the solution. And this is E33. I forgot to make these changes, but here we have taken the consideration. That is, and E33 is actually indeterminate because we do not get an equation involving E33. And if we could take E33 to be 0, then it would be a trivial one. So we write it, and the I, if we write the I normalized eigenvector, it will be in matrix 0, 0, 1. So which is perpendicular to both E1 and E2. So we see what the directions are. Firstly, E1 is directed along the 1, 1 direction, that is, it is in the direction of OB, and this E2 either directed in this direction or in this direction. We write, so this is the direction of E2. So one is along this diagonal, other one is another this diagonal, and E3 is along z-axis. These are the principal axes that we have obtained starting from this. Remember that for this system, a simple consideration, symmetry consideration, gives us a set of principal axes. If we set coordinate system like this is the square lamina, this is x-axis, y-axis, and this is the z-axis, then we will get a principal axis. But this technique that we have developed is a general technique, and if we somehow constructed a moment of inertia tensor in any coordinate system, then we can adapt the procedure of matrix diagonalization to get the principal axis. Another way of getting it is the fact that if we know the moment of inertia in any coordinate system, as for example this S coordinate system, then we can get their projection or moment of inertia about an axis having direction n cap. So if we want to get moment of inertia about an axis characterized by a unit vector n, then it is moment of inertia n, where this ket n is the cos alpha, cos beta, cos gamma, that is, these are the direction cosine of the axis n cap. If we consider this E1 direction, for E1 direction, n cap, so this direction makes angle 45 degree with x-axis and 45 degree with y-axis. So this is cos 45, and y-axis, the angle made with the y-axis is cos 90. So the matrix is 1, taken 1 by root 2 out, 1, 1, 0. So if we come to I1, this is, we call it N1, so this is N1, I, N1. For there are 2 root 2, so this is half, this is 1, 1, 0. Then in terms of this 1 by 3, 1 by 4, 0, minus 1 by 4, 1 by 3, 0, 0, 0, 2 by 3 multiplied by 1, 1, 0. If we first, this matrix multiplication gives us 1 by 3 minus 1 by 4, that is 1 by 12. This is again 1 by 12, and this is 0. So if we take 12 out, so 1 upon 24, and then 1 multiplied by 1, so this is 2, so this is 1 by 12, this eigenvalue. And for E2, if we consider E2, it makes 45 degree angle with x-axis and 135 degree angle with y-axis. So for E2 we have, this is N2, this is 135 degree. So this is minus 1. and consequently we get I2 is equal to N2. This is minus 1, this is minus 1. So first matrix product gives us half 1 minus 1 0, then this multiplied by 1 by 3 and 1 by 3 plus 1 by 4, 1 by 3 plus 1 by 4, so this is 12, 7 by 12, 7 by 12, this part, this is plus and this is plus, again 7 by 12, 0. If we take 12 common, so this is 1 upon 24, 1, no, this is minus, this multiplied by this minus and this multiplied by minus. So 12 taken out, so this multiplied by 1, 7, and this is again 7, so this is 14. So if we 7 by 12, this is this one. And for E3, you see that for E3 we are to find out the direction. This E3 makes 90-degree angle with x-axis and 90-degree angle with y-axis and 0 angle with z-axis. So this is 90, 90, 0. 90, 90, 0. So the angle, this transformation matrix is 0, 0, 1. So I3 is N3, N3, so this is, no half is there, 0, 0, 1. This is again 0, 0, 1. So we get 0, 0, 1, and this is 0. This line, this multiplied by this is 0, and this is only 2/3. And when we multiply this, we get simply 2/3, the third eigenvalue. So the thing that we have learned how to get the eigenvalues and the corresponding eigenvectors of the moment of inertia tensor as evaluated in any coordinate system. And then the eigenvalue should be the moment projection of this moment of inertia tensor in the respective directions, and we have developed or narrated a method which allows us to find out the components of moment of inertia along the respective axis of rotation. Now we shall go to the another case. That is the example 3. We shall consider a uniform cube. So our next example is a uniform cube of side A and mass we choose the cube like this. So we choose the coordinate system in this fashion. This is y, z, this is x, and origin is at that corner. So the cube is OABC, DEFG. So the mass m, so the density is m by a cube. If we could choose the coordinate system which is parallel to this coordinate system and centered at the CM, then it would give you a set of principal axis. But here we have deliberately chosen origin at one of its corner, and we want to find out what is the value of moment of inertia, tensor and other things. So Ix is equal to integration over V rho is uniform times y square plus z square. So if we write it explicitly, rho taken out, this is dx from 0 to a y square dy from 0 to a dz from 0 to a and multiplied by 2, because one we have evaluated this part, not plus z part, and if we perform this part, just the row between x and y and z gets interchanged, so we have written it as 2. So this is 2 rho, it is a, it is 1/3 a cube, and this is a. So rho a cube is m, and this is 2/3 m a square. This is also the value of Iyy and Izz due to symmetry. So I get the values. And the product moment of inertia coming to Ixy is equal to minus rho xy dv which is minus rho x dx y dy dz 0 to a 0 to a. This is half a square, half a square, so this is minus 1/4 rho e to the power 5. So this is minus 1/4 m square. So we get the moment of inertia tensor in this coordinate system. So the moment of inertia tensor is two-third minus 1/4 minus 1/4 minus 1/4 2/3 minus 1/4 minus 1/4 minus 1/4 2/3. Which, as before, we choose the AI, the eigenvalues, as AI is equal to lambda I m square. So that lambda I are the dimensionless eigenvalues. So the secular equation is 2/3 minus lambda minus 1/4 minus 1/4 minus 1/4 2/3 minus lambda minus 1/4 this is equal to 0. We first change the rho 1 prime is equal to rho r1 minus r2. So the first term is 2/3 minus lambda plus 1/4. So this is 2/3 plus 1/4 is equal to 12. So this is, if we do this on performance, this is 11/12 lambda, 11/12 minus lambda. This part is minus 11/12 lambda. This is 0. This is minus 1/4. 2/3 minus lambda minus 1/4. We further write R3 prime is equal to R3 minus R2, sorry, R3 minus R2. So this is 0. This part will be minus 11 by 12 minus lambda, and this will be 11 by 12 minus lambda. This is equal to 0. Now the evaluation is simple. If we carry out the calculation, only we need to calculate this multiplied by that, and the values that we get out of this, I am skipping the calculation and just putting the values. The values that we get is there are two repeated roots, 1/6, 1/6, and the other one is (11 by 12). So these are the three roots. Now if we put first one, this is I1 is equal to lambda 1 ms square is equal to 1 by 6 ms square, and coming to this circular equation we get 2 by 3 minus 1/6 minus 1 by 4 minus 1 by 4 minus 1 by 4. This is 2 by 3 minus 1 by 6 minus 1/4. Wrongly, the other root is 11 by 12. So this part, this is 2 by 3 minus 1 by 6. This is 1 by 6. So this is 4 minus 1, 4 minus 1 is 3, so this is half. This is half. So we get it. Half, this is half, this is half, this is half. If we carry out the first row operation, we get E11 is equal to 2 times E21 plus E31. For the second row operation, we get E21 is equal to 2 times E31 E11. And for this third row operation, we get E31 is equal to 2 times E11 plus E21. If we add these up, we get E11 plus E21 plus E31 is equal to 0. This is the condition. Sorry, this is the relation we get. The solution, the possible solution of this is E11 is equal to E21 is equal to E31, so that the eigenvector E1 eigenvector is 1 by root 3 1 1 1. This is the eigenvector. So this actually represents this direction, this body diagonal direction OF. This is the direction of OF, which is the direction of OF, the body diagonal. Now coming to the other roots. These roots are degenerate because this is lambda 2 and this is lambda 3, but when we put this in this equation, we do not get any extra information. So for I is equal to I2, I is equal to I2 is equal to 11 by 12 ma square. The matrix becomes, first one is the diagonal terms. Let us consider the diagonal terms. This is 2 by 3 minus 11 by 12. So this is 12. So this is 8 minus 11. So minus 1 upon 4. So these terms are minus 1 upon 4. So this is, we have minus 1 upon 4, minus 1 upon 4, minus 1 upon 4. This E12, E22, E32 is equal to 0. So the relation that we get is E12 plus E22 plus E32 is equal to 0. And for the other one, I will have also this is the relation. To know the eigenvector E2, from this we get the eigenvector E2, and from this will give us E3. To know these two, we need to know the 6 conditions, out of which only one thing is given. One relation is given, because these two are not different relations but the simple relation. The way out is that we know that the eigenvectors E1, E2, E3 are perpendicular to each other. When we write this relation E1 dot E2 is equal to 0, this comes out to be E12 plus E22 plus E32 is 32, which is nothing but this. So this does not give us any new information. The only thing that we get is if we write E2, E3, this gives us, this multiplied by this E12, E13 plus E22 plus E23 plus E32, E33 is equal to 0. This is another condition. So we have only 2 conditions at our hand. And we need to know 6 quantities. So we are at liberty to choose 4 at our will and to choose the rest. Before going to this, we first know what this condition implies. This implies a plane. It is a plane perpendicular to E1, because it is a plane which is perpendicular to the body diagonal OF. So actually we get that this E2, E3 vector must lie in the plane. So this is the equation of the plane DAC. This is the plane DAC. So this E2, E3 vector lies in DAC plane, and Since it is perpendicular to OF, we need not to consider worry much about this. The only thing is that E1 and E2 must be E1 and E2 and E3 must be mutually perpendicular. If choice is may be done in this way, we write, to simplify notation, we write E2 is equal to A2 B2 C2 and E3 is equal to A3 B3 C3. Of these 6 we can choose 4 at our will. Out of 6, A2 B2 C2 A3 B3 C3, 4 can be chosen. 4 can be chosen arbitrarily as there are only 2 independent conditions are available. We choose our choices. C1 is equal to C2 is equal to 1 and C1, C2 is equal to 1 and S is equal to B2. And the eigenvector that we shall get out of this is E2 is equal to 1 upon root 6, 1 upon root 6 minus 2, 1, 1, minus 2, 1, 1, and E3 is equal to 1 upon root 6, 1 minus 2, 1. Once again, these choices are not unique. We can choose any 4 and then we get the other relations too. Actually, there were 3 conditions. 3 because there were 3 relations. As there are only 3 relations. Actually, 3 relation is A1 B1 A1 plus B1 plus C, A2 plus B2 plus C2 is equal to 0, A3 plus B3 plus C3 is equal to 0, and A2 A3 plus B2 B3 plus C2 C3 is equal to 0. These were the 3 relations. So these are the eigenvectors, and we can, if we choose this one, this we see the angles that this direction makes with the coordinate system can be ascertained, and we get the corresponding values of moment of inertia I1. So this technique of calculating moment of inertia for a rigid body is applicable for symmetric bodies as well as asymmetric bodies. For asymmetric bodies, it is become very difficult to find out the moment of inertia by inspection. In that case, this method works.